Welcome to Essence of Science. And today we are going to talk about time. No, you're doing this.
Only I have.
No, you have a watch. You're the only person you have a watch. When did we start having watches on our wrists?
I would say, I'm guessing entirely. I don't really have a basis for this, but I will go with 1800s, maybe when we could get a little bit closer to.
Nope.
I will say not on our wrist. That is far more advanced. Before that, people had it in their pocket, right? That is
A gentleman would have a watch in their pocket with that
pocket
chain
Yeah.
and so on and so forth. Putting it on your wrist, that was ungentlemanly.
You
When-
animal.
when-
Put that in your pocket.
But when did we start having that? When did it become acceptable to put it on your wrist?
All right, second guess. It's going to be 1920s.
You are very close.
I'll go 1950.
Huh?
I'll go 1950.
No,
No.
no. No, for a long time, you couldn't have anything that tells you the time that wasn't a cloth, like a big furniture
Gotcha,
piece.
yeah.
Okay, we will get back to that. But then, in one country, they got really good at making timepieces. You know what country it is?
Was that Germany or Switzerland?
Switzerland, Swiss. And then they got it smaller and smaller, so it was still big, but still could fit in your pocket or in your wrist, but you wouldn't put it on your wrist. That was like, very, I would say, low class.
Was it because it's like rude to show people that you care about the time?
That you can afford to have something that you're like, have you seen people who have blinks?
Yeah.
That was the bling.
Gold in your teeth, material wealth displays.
Yeah.
Okay.
Gotcha. Okay.
So, but it became acceptable at the First World War. Why? Because the officers had to have their both hands to adjust the artillery and so on, and they had to see without have to use one of their hands. So then it became acceptable for a gentleman to put a timepiece on their hand. Isn't that interesting?
Yeah.
That having a watch on your wrist was considered rude and not really a gentlemanly things to do.
History of stuff like that's always interesting because I actually, when I do wear a watch, seldom as it is now because I broke it a while back, when emergency department things, but I would always wear it on the inside of my wrist. People would say that really you only do that if you're a scuba diver or something, and I just, why? Like, why does it matter if it's on the outside or the inside? It's
so you, like, as long as you're watching the time.
Yeah.
It's about saying the time, and that's why I don't have a watch, because I have a cell phone that is my watch, my cell phone, my camera, my calendar, and so on.
I'm sure you would rather lose your left leg than that phone. So
no, I wouldn't go that far.
Access to a phone?
I can. I mean, I still can replace many of the things with the other things but we are getting close.
We can get you a new leg, Doctor. But maybe this one could have a cell phone holster on it.
yeah, that's tempting. That's really tempting now. No, but this is, so we are talking about the 1914 when the First World War started. These artillery officers and so on. They have before that they had something in their pocket that tells the time. But that was already a revolution. Okay? As a matter of fact, in the Admiralty or in England, for a long time, they had a problem. The problem was you had all these astronomical, charts and so on. But to be able to say where you are, you had to have a very efficient piece that tells you the time, or at least it tells you how much time has lapsed. So, what do you guys know about the sextant? What is a sextant?
I don't know anything about this. You could have just made that term up.
My guess is like 60 second A minute?
No,
Okay, then.
sextant
Next
is
thing.
an astronomical device that
Oh.
you look at the star and you look at the horizon and you can tell by adjusting few things. Look it up. It's a masterpiece of
Didn't navigators used to use that on ships quite a bit?
yes.
Okay.
Yeah.
Yeah, sextant.
I've seen that. I never knew the name. I always just thought it was some kooky thing.
Yeah. So you adjust it to the horizon, and there's another piece you put it, adjust it to a star or something that in the sky,
Mhm.
and literally, you measure an angle, and then you measure that angle after a certain time period again, and you know how much Earth has
Mm.
moved. Based on those angles, you can say what is your latitude and altitude, or how far north from
Mhm.
equator you
Yeah.
are, because they change based on table they had made. That certain star like North Star would change that much. The other star, the other constellation would change that much. You could tell on the Earth you are, but to be able to do that, you had to know, like after 5 minutes, you had to know after 5 minutes what that angle is. But how do you measure 5 minutes? If you don't have that watch or cell phone, how do you say 5 minutes has passed or 15 minutes? They used to do it even longer because longer periods would give you better angle and so on. But let's go 1,000 years back. How do you measure 5 minutes 1,000 years ago?
Man, that just the internal clock. That's all I got. You'd have to guess. I can't imagine any empirical way to say, unless somebody's counting.
No, they could. They could. Surprisingly, they could.
Really? Heartbeat, like 60 heartbeat?
You're on something. You're on something. See, I love these conversations. Galileo, 1400, was a very smart boy. He's sitting in the church, and lots of smart boys, he's in the church, he's bored. Instead of listening to the sermon, he's looking at a huge chandelier. And in those days, the wind had really, glass was expensive and so on, so it's all open. So wind is coming and the chandelier is swinging. Like a pendulum.
I see where we're going. Okay.
And he looks at that and he says, independent of how much wind is around and how much swing this chandelier has, it seems that it needs the same amount of time to go back and forth. But this chandelier is big, on a long rope. So meaning that it it takes a while to goes back and forth. He want to test that theory. Is it truly just, am I just making this up? Or does it really independent if it goes like 3 feet or 30 feet, it still need the same amount of time? How would you do that? How do you measure if you don't have a watch? As a matter of fact, that is how watches are made. Before him, you could have a sundial. You put something at certain angle. It has to be certain angle to the sun, depending on how far you are from the north, from the equator. If you don't have the right angle, you don't get a good result. But if you have the right angle, as a matter of fact, it has to be the angle of how the Earth is rotating in that specific location to give you best sundial. But they figured it out. They could say that you put something down there in the sundial. That's what the sundial. They are not like a stick. They are like an angle, right?
Yeah, like basically almost a right triangle there.
Yeah, like a triangle, and that triangle changes depending on how far you're from north you are. Okay. So if you're in Europe, maybe you can use the same thing more or less, but that actually depends on that. But then you see on the sundial that 5 minutes later, sun is somewhere else. The shadow is somewhere else. So you could. So the idea of having a day, 24 hours, every hour 60 minutes, every minute 60 seconds. As a matter of fact, a minute was a primum secundum. That's why second is second. Because the first division was minute, second division was second, And now with the minute, we they drop the primum, and the minute meaning that division, first division, we just say minute. But then second, we say secundum, the second division. We still keep that. So we had the idea of they are, and why we did that way and not other way has something to do with the Babylonian. I'm not going to go there because this is not the history of time. This is the science of time. So Galileo, 1400 something, sitting there bored and sees the pendulum going back and forth. How does he test that hypothesis that independent of how much it takes same amount of time for the chandelier to go back and forth? Then he invented the pendulum. How does he?
My only guess would be
you said that he measuring his heart rate.
Oh,
yeah.
He literally everybody knows. You feel it. Okay, we didn't understand much about that, but he's a smart boy. He understand whatever it is, his heart is beating at the regular intervals, and he tested with that hypothesis with his heartbeat, and he says, yeah, it seems that is truly how long it takes for the chandelier to go back and forth. But see, somebody else sees that and just move on.
Yeah. Oh, that's weird.
Not Galileo. Not Galileo. He doesn't move on. He goes put that to the test that the only thing that changes the time interval for pendulum to go back and forth is how far it has to swing. Longer takes longer. Shorter. That's do you guys have ever seen a truly pendulum clock?
Yep. I think
so.
I've seen.
Honestly, they're pretty long.
Yeah.
The weight doesn't matter. Absolutely doesn't matter. How far they go back and forth doesn't matter. Only the length matters. So they have something, and the length is the center of mass. The center of the mass, because you can have something that looks fancy looking. It doesn't matter if 350 yards. But if the center of mass of that 350 yard thing is in a location, that length is directly related to how long it takes. So they have a screw that you can bring up or down the center of mass and then adjust it through second. Okay?
2 seconds.
To a true second.
Oh, to a
if
true
it
second.
doesn't, there's a screw that you can lift up and bring down a weight on the pendulum, and that if you're like every day you are 5 minutes behind, you just
turn
a little screw and then go up and down and adjust it. So, and that's 1400 something, 1500. Now all of a sudden we have these pendulum clocks. They're so much better than sundial. Now we have a problem. In the ship, in the night, there's no sun, no shadows. And even if there is, where's the shadow? And that's
it's kind of moving.
The pendulum only works if you're stationary.
Yeah, on the sea, when it's shaking, it's just...
Then the pendulum is useless.
Yeah.
So the British Admiralty or Parliament put the thing out. Whoever can create a chronometer, something that measures the times accurately at sea, because we need that to do all those things. Or if everything is calm, and in the day I can use a sundial. If it's calm at night, I can use a pendulum watch, but it's not reliable. How do we reliably measure that? They need a chronometer. Even if it doesn't say the exact time, you can say it's 15 minutes has passed. Because with that, you can look at the stars, you can say where you are, and British are going to rape the entire planet with their colonialism. They are depending on their ships. They need that. They
need to know where it's going and when.
£20,000 price on that, which is about $4 million today. Who can invent that? And somebody does it. How does he do that? Same principle that mechanical watch works even now.
The spring?
Yes. spring and a wheel. Spring and a wheel. A wheel, see, the problem with all these things is you just need the reliable increments. Okay? And what do they find out? That is why all of a sudden we could have a watch on your hand. They find out if that piece is smaller, the other motion around it affected less, the same way that if you have 500 kilogram and you have to move it, it's harder than if you have a 0.5 gram.
Yeah.
So Swiss people find out that actually, so they find out that there's something, a wheel that goes back and forth with the spring, that swinging of the wheel is equal to swinging of the pendulum. And if you encase it with a spring and it can go smoothly only in one direction and make it small, it's not as affected by motion outside of it as a pendulum.
Man, that's...
And smaller, the better, because smaller has less than the surrounding motion has less effect on a smaller thing. See,
there's less surface
still has
friction
some.
and all this stuff.
Well, see, the pendulum. The problem is that it's just the gravity is moving it, and the gravity changes depending on if you're going up and down. Like if you're in an elevator, the gravity and so on, effect of the gravity changes. Now you compensate that with the spring, and then still gravity is still working, but if you reduce the weight, the gravity's action is so much less that the spring action is like 500 times, 1,000 times more than the gravity. And they figured out that, yes, we can make a chronometer, but if it's smaller, it's actually better, it's more accurate because the gravity affected less. So, and then Swiss got really, really good at it, and then made it smaller and smaller, then you could put it in your pocket, but still, it was a fashion thing that then now you can put it on your hand. So, time. We still haven't talked about, we just talked about passing of the time.
Yeah.
What is time?
Well, there's a couple different ways. I mean, it's just the moving of one moment to the next in some, but like the way that we measure it is usually just how much we're rotating.
How do you notice time has passed?
Just not where I was before, but I mean, that's a different dimension that we kind of perceive it as. So,
Jimmy, what's time?
I have no idea. Time is like something that's
You just answered that. We don't know what time is.
Yeah.
We just know what passing of the time is.
Yeah, passing of the time.
We cannot, for a long time, we had a Newtonian view of time. That is linear. It goes from one moment to another in equal intervals across the universe for everybody the same rate. We know that's not the case. We know that time and space are intertwined in a very complicated way that you can pass in one space-time at certain total speed, but if you go in one direction, like imagine when you're stationary completely, meaning that nothing really moves, which doesn't exist, by the way. There's nothing. Are you moving right now or not?
Through space? Yes.
No, first of all, the Earth is turning. You're probably at equator. A person at equator is moving about 1,000 miles an hour with the Earth, right?
Yeah.
You want to calculate it?
I don't know if I could.
1,000 miles an hour is about 1,600 kilometers an hour. Earth's circumference is 40,000 kilometers. But that means that in one day, you're back where you were. So in one day, it has to move 40,000 kilometers, which is about 1,000 miles an hour.
Makes sense.
Right?
Yes, that makes sense.
24 hours.
That is so simple.
Yeah.
Okay?
You just go back to a same place.
Simplicity, yeah.
Takes 24 hours to go that distance.
Yeah.
Yeah.
So that person on equator moves 1,000 miles an hour. That person, same person, at North Pole moving how much?
North Pole, 0.
Yeah.
Almost 0, because it's still rotating.
But
It's rotating around his own
a
axis.
lot less than
Yeah,
what we are moving.
almost 0. We are, let's say, somewhere between. So we are right now, just in Earth, you're moving about 500 miles an hour, the speed of a passenger jet. So when you take off from Minneapolis, go to Frankfurt, what you do actually, you take off, you stay stationary in the air, the Earth under you moves, then you come back and land. That's what's really happening. Compared to the
Running backwards
total
on the
thing-
treadmill.
No, you just take off in the air. You just try to stay there against the air that's moving. The Earth underneath. That's why actually, literally, when you go from Frankfurt to United States, okay, you barely lose any time. You come almost like you're flying for 9 hours, but actually, the time difference is 2 hours. Okay, how is the Earth moving?
Rotating.
Rotating on the line.
Rotating. And imagine United States being a monster eating the rest of the world. United States is actually moving toward east. Okay? That's why sun goes from east to west, because Earth is moving from west to east. Okay?
Yeah.
Making that sense?
Yeah.
So
checks.
In that case, when you are going from here to Germany, you have to go up and go against. That's why it takes longer to go east than to come west. But when you're coming from east to west, you just have to get up and stay there until the Earth under you approaches you, and then you come and land. Okay?
Let the Earth do all the work.
So you're moving right now in space-time, just on Earth. Now, that gets even more complex, because Earth is moving around at what speed?
Oh, don't know.
Like about, I think, 16,000 miles an hour. But that's not it. Our solar system is turning around the center of the galaxy. What's that speed? Like hundreds of thousands of miles an hour. Hundreds of thousands of miles an hour.
All these little seesaws just twirling us around.
So
we are flying in the universe.
Nothing standing still. So you will always have a speed in the space, but then you add to that, but let's say you were completely stationary in space. Then all your speed would go in time.
I just can't help to think, if we really have something here, for example, this watch that is 100% stable, not moving in the
at all, in the whole universe, okay?
Then in a snap, it's gone.
Yes. Yes. Yes.
Yeah.
So all that time machine things are nonsense, because to go to a time machine and go back in time. Well, if you go a second back in time, you're in the middle of the space. Nothing is really there.
Yeah.
You get that part?
This crushes my childhood dream. I always think time traveling is real. Now,
So in 1 second, you have left the Earth, you have left the solar thing, and in less than a few seconds, you have left our galaxy. If you are truly stationary in the universe. So you're gone. You're suffocated.
It's over.
Died.
Ice gone.
Okay. But beyond that, you have a momentum. If you just all of a sudden are stationary, all your atoms will smash to each other. That is how fast you're going. You will be squeezed to nothingness if you just become stationary. The change in acceleration, what is the change in acceleration that is deadly to human body? You would be surprised how ridiculously low it is. No, you drive a car. Okay, you drive a car. What is the speed of a car that is considered, if you have an impact there, is deadly?
Like 50 or 40 miles an hour, sort of thing like that.
What do you think?
I don't know. Playing is fast.
Okay, if you hit a concrete wall at 30 kilometers an hour, meaning about 18 miles an hour, It's 100% deadly.
18 mile per hour.
18 miles an hour, you hit a concrete wall, and you don't have airbag, you don't have nothing else, you don't have a car that will. You go with 18 miles an hour, you hit a wall, 100% you die.
Maybe the speed limit in school zone should be a little lower then.
That's really slow. Like,
Aren't you surprised?
Yeah.
Yeah, because I mean, like,
So why don't people die with car accidents?
Seatbelt. Always wear seatbelt.
Now, first of all, barely ever somebody hit the wall. They hit the brake. By the time they hit the wall, that may be 10 miles, 15 miles an hour. Then they have the airbags, seatbelt,
the crumple zone
and
of
then
the
the
car.
crumble zone of the car, all the things, and so on and so forth and so forth.
Yeah, and they can usually transfer some of that momentum to the thing that they hit. You know,
Yeah.
well,
Yeah.
not really. But.
You gotta hit the car first, and then it's.
Yes, it all takes time and so on, but so you can imagine that you're going 100,000 miles an hour.
Ooh.
I won't even be a mist at that point.
So you're talking about time. So you're moving in space. So whatever you're not using in space goes to motion in the time because they're intertwined. But now all of a sudden, imagine you're moving in space faster and faster. Then there's less left for it is a zero-sum game, meaning that faster you move in space, slower time would become for you.
Yes.
Okay? For you, for an external observer. Okay? So time is something that we understand only the passage of it, but not really true nature of it. So you were struggling, Jimmy, saying, and then you said, I don't know. Because nobody knows what really time is. We have some ideas about time. Okay?
So time for an insect is different for time for a human. Because they, as I know, they can process a lot of information than us, and they have so many eyes, this kind of stuff. So
time is always as well, the passage of time is, even psychology of the time is very different for people. Like I'm listening to my audiobooks at 2.3 speed. And people go crazy when they listen to that. But then I met somebody who's listened to that at 4 times. I was crazy at that. So, and your brain, how you process the time as well is but that is psychology of the time. Yeah. Yes, it is perceived differently by different people.
I think Amanda would have loved this part, but like cats, for example, they don't really understand time. So whether it's, they understand markers in time. So I eat around this motion. So I have this internal clock of like, I want to eat now sort of deal. But a lot of them, they don't know if you picked them up 3 years ago or 3 seconds ago. They just don't have that passage to them.
But I'm not a cat, so I don't know how they perceive the time. There are some things, we should talk about the psychology of the time, and especially across the biology. But so, space-time, something is happening though, something is different. Like, imagine, like, if I move from Chicago to Minneapolis, my car is moving, 6 hours later, I am in Minneapolis, and something has passed. It's not the same time. Sun is going down. I'm not in the same place. It's different. It's a different city. Something has changed. Now, imagine you're in the middle of the vacuum in the space. There's no up and down. There is nothing rotating. There is no sun going up and down. But there is still something happening. There is something that is different from the moment to the moment to the moment. Even if you don't have a clock, then you're still thinking because your biology, your molecules, your thing is still something happening. You may be confused and lost. Like people who go to mines and so on, they lose their circadian. Again, not the biology, but there's still something happening there. Okay, something is passing. What is that thing that's passing? What is it? You don't understand it, but you have some ideas about what actual time is. Now, there is a good understanding about it's so-called Laplace. Have you guys heard of Laplace or Laplace Demon?
No.
Okay, well, let's go to 1800. Until then, you understand the sun going back and forth. You understand that you need a chronometer. That you understand, and for you, time is still an equal intervals. Something's passing. Is something in the fabric of the nature. It is just from moment 1 second, 1 second, 1 second, and you add them and you calculate. Everything is working beautifully. You calculate. As a matter of fact, they need a watch and chronometer to adjust the artillery. You understand at this angle, it has this trajectory. It takes that many minutes or second to go for the projectile to go over the hill and hit something else. You have to calculate against Earth's gravity how long you need to send it up before having this trajectory and go hit where you need it to go. Okay, that is why it was gentlemanly now all of a sudden to have the watch on your wrist so you can kill people. Okay,
that's always how we do it, you know.
That's always how we do it. Okay, something is happening, but we didn't have a good understanding about what that is. But we got better and better to measuring the intervals,
And that is called time.
and that is got time. Now we got so good at it that now we have these atomic watches. Now you get the atomic watch here. It shows you the time interval of going this speed. You put that same watch, you bring it 2 feet up. All of a sudden, you see these two watches are not matching anymore. Because this one is closer to the center of gravity of the Earth. As a matter of fact, there is now new method to measure the height of the things. You have these super accurate watches. Depending on how high up and down you are, you can say how far you are from the center of the Earth. We are so good at it because when was the last time you guys used GPS?
Every day.
Every day almost, right?
Yeah.
So there are these satellites. They are not stationary. They're just moving around. But they communicate with each other and they know exactly where they are because they communicate with each other. And then they send you a time. And then you get that time from signal from 3 or 4. You get it from three satellites, and the fourth is for confirmation. And then this clock says the time is this. This satellite says the time is this. The other one says time is that. The other one's time is that. Knowing how speed the electromagnetic waves are, you know your exact distance from each of those 3 satellites. The fourth is for confirmation. And then you calculate your distance from those 3 satellites at the time they send the information. And that's how you calculate your location on the Earth. That's what GPS is.
Oh,
Thank you, Phil. That's a lot of work I don't want to do.
that's a lot of work.
That's a lot of work. But it happens in a fraction of a second. How accurate is GPS?
Oh, I don't think GPS is accurate. Usually I just drive there and
It's
Well,
You
incredibly
guys are
accurate
so
versus-
spoiled.
when I,
You
when I
guys are
drive
s-
past the road and they tell me turn right. So it's not accurate.
No, generally GPS is accurate within inches in the United States. If you have the right instrument, you can be accurate within inch in the United States. Obviously, our phones, they have delays and this and that and so on. And then by the time it tells you where you are somewhere else and so on. But generally, GPS can be accurate within inches. If you wouldn't calculate that, if the satellite is higher, the time is going what? Faster or slower? Faster. And if you wouldn't calculate that, if the satellite is moving this speed, that time is going what? Slower or faster? If you go faster, is the time going faster or slower?
You go faster, time goes slower.
Exactly, because you're using more in the time than if you're going more of the space, there's less for the time. If you wouldn't calculate that into the GPS, your accuracy would be miles. You would be accurate within miles, not within inches. So thank you, Einstein, for your relativity theory, because all of us would be lost. If you think just a few meter is wrong, and I'm so disappointed.
I'm just picturing the classic RV map on the dashboard.
Yeah.
Going, I think we're. You'd hate it.
So, but we still haven't talked about what is actually time. We don't know if time comes through interval like everything else, like in quantum theory, if it's a discrete package of time or not. Maybe there is, maybe there isn't. We are approaching that with with this so-called Planck constant, which says that the space is in discrete intervals. How do we know that? There is a chunk of space, 10 power minus 35 meter, where the laws of nature, they don't make sense anymore. Like, you cannot increase the energy of that space with the electromagnetic wave. Don't make sense anymore. Like that, you go from the radio visual light to radio waves to X-rays and so on, and you go up and up. There's not much you really. The laws, the formulas, they don't make sense anymore. So we do things. The space comes in chunks, and considering the space time are intertwined, at that point as well, less time doesn't make sense, because that's the smallest interval electromagnetic wave can pass. So it might be a chunk of time passing that we understand, but it is unbelievably, something that we use every day. It's unbelievably how little we understand really what it is. Now let's take laws of nature like Newton. This is like the billiard table or pool table.
Yeah.
And then imagine, let's say this is one and this is the other one. One hit the other one, and then this go depending on their weight and so on. Billiard, they're all the same. So meaning that if this hits this stops, this moves, right?
Yep.
If they're the same, and if they're head on.
Yep.
Okay? Now, if I make it the reverse, this comes, hit this stops, and this moves. Or if I reverse the move, if I take a video and I reverse the video, could you tell me what happened when I do this? Or if I show you this? Which one is real? Which one is the reverse? Can you say that?
No.
I mean, if it was frictionless, no.
No.
Yeah, we don't know.
You couldn't. You just mentioned it naturally. If there's a friction, what do you notice in the laws of nature? The laws of nature, you notice when you hit this, some of the energy goes into friction. So speed of this is less than speed of this, if they're exactly equal weight. But if there is no friction, there's no way to say that, meaning that for all we know, most of the laws of the nature are reversible. Nature doesn't care if this hit that or this hit that. Like, you think sun going up and down is normal and so on, that comes east and south. There's nothing in the, we just call it east and west. It could be as well in the southern hemisphere that sun goes in different direction and so on. You can reverse that movie and nobody can tell. But in nature, though, it's not the same thing, right? I know. You opened the door and came in. You didn't walk backward.
Yeah.
Close the door and so on. But why is it that our regular understanding of the time is so linear, whereas nature doesn't care about, everything is reversible in nature?
The scale, it's just the scale of time is too big so that you can ignore it.
That was a philosophical thing in 1800 that Newton, after they had the laws of the Newton laws of motion, they say, if you know the mass and the momentum of every atom in the universe, you would know the entire history of the future and entire history of the past. Meaning that you just need to know how things are now, but then you would know everything about the future and past.
You can calculate it now.
You can calculate it everything. Now, I'm telling you the secret, the computer who could calculate that is as big as the universe. As a matter of fact, universe is the computer who's calculating
Yeah.
how these motions are acting on each other. Because there are so many things, like somebody did that calculation on a pool table. Imagine you hit the pool table and you calculate at what angle when you hit another ball, how it's going to behave. That's easy. And you see on YouTube as well, some fake, some real, how people calculate 2 or 3 steps. But let me tell you something. If you want to calculate by the 9th hit, or even by the 8th hit, how everything is going to react there, you have to calculate the weight of the hydrogen atom on the other side of the universe. You have to bring that in your calculation. And that's just a pool table. So you understand, yes, the complexity is one of the reasons, but we always see, we put coffee, creamer in the coffee, but we never see creamer coming out of the coffee. Okay? So the complexity is one factor. There's a different name for that complexity. You get a chocolate bar. If whoever says, what's the name of that complexity that makes the arrow of time appear always in one direction for us, there's a name for that complexity. Entropy. It's called entropy.
Entropy.
Yes. What is entropy?
The dispersion of energy.
It is one of the biggest things that really makes time sense to us. Entropy. They say entropy always is increasing. Entropy is a measure of disorder.
Randomness in the system. Kind of deal.
Like you have a hot coffee, you put it on this table, it is lots of heat in this. The atom in the coffee are moving so fast, but then eventually those atoms make the atom of the air around it move faster. Eventually, after few hours, all the atoms in this room are moving at the same speed. You cannot, based on their actual heat, that's what heat is, just the speed of the atom moving, okay? 300 years ago, we thought there's something called caloric, that is a fact of nature, that something in the air, in the ether, that it makes things hot and so on. But now we know it's all bullshit. It's just the speed of the atom that makes something hotter and or less hot. So, but we put the coffee here, after a few hours, all the atoms in this room are moving at the same speed, which is their temperature.
Temperature go up. The room temperature.
Except atom in my body are, because this temperature of this room is like 26 centigrade, 100 Fahrenheit. No, it's 70 Fahrenheit, and I'm 100 or 37.5 centigrade. So my atoms are moving faster, and they bump into the air here. But if I die, and then eventually I'm the same temperature, okay? The process of getting that higher speed of my body to the surrounding air is called entropy. And it goes in the universe, it goes only in one direction. Everything becomes equal, and that's another thing we need to talk about, what entropy is. But the entropy is what makes us to believe there's only one arrow of time, because it goes in the whole universe. Entropy goes only in one direction, at least what appears to us to be that way, meaning that we see always hot go disperse to the colder area. Everything becomes equal, becomes less distinguishable, and never goes back. And that actually, that increase in entropy makes the arrow of time for us unidirectional. Now, let's come back to that. And I think if you understand that, you understand as well the entropy better. Has nothing to do with time, but it's so intertwined, but I want to really mention it here. What do we get from sun?
Heat.
Heat, energy. Yeah, heat energy
Yeah.
equivalent, right? How much of the energy of the sun that comes to the earth are we sending back to space?
Like how much we reflect, kind of deal.
Yeah. How much do we keep? How much we use some of the energy, right? How much of the energy of the sun are we reflecting back to the universe, to the space?
My guess, 90%.
I was going to say
90%?
70.
70. So you're saying we keep 30%, because it makes sense, right? Plants grow and so on and so on. But you say 10%. We keep 10% of the energy of the sun. You say 30%. Think about that. Sun hits the earth day after day, year after year, millennia after millennia. We keep 30% of the energy that comes to us.
Oh, that's too much. Let's change it to 99.9.
99.9%.
Is reflected away.
After calculate that, after 1 month, all the stones would be molten. If you would keep 1% of the energy of the sun that comes in after 1 month, there's a formula, you can calculate it. Everything would be molten on the surface of the planet.
Okay, we need
Let
to
me ask you
keep
the
this.
question.
Look, no, this convinced me that we need to put a Dyson sphere around the sun. We need to harvest that. That's so much energy just wasted. I've just learned.
No, there are lots of energy there, but absolutely, we come back to Dyson sphere. But same question. How much of the energy of the sun do we reflect back to the space?
All right, I'm going to change my answer.
From
All of it.
70%?
100%. We keep them.
What do you think?
Very close to 100%.
I say 100%. If you take me to, well, I guess this is understanding time as a linear, so forgive me, everybody. But if we go to the end of time, we will have kept none of it. So
Zero.
I go with,
Zero.
we get rid of 100%.
0% of we keep 0% of the sun's energy. So what are we using then? If you are reflecting, no, this is fact. If you would keep 0.00001% of the sun's energy, within certain amount of time, eventually, we would heat up and evaporate. Okay? So we are reflecting 100%. So again, first question, remember I asked you, what is sun is giving us? Energy?
Alone?
Is he just borrow? Are we just borrowing?
Yeah, we're taking a small loan of disorder from the sun.
After
That's
we
what
use
it
it,
is.
That is what it is. Small part of not disorder. We get the order from the sun. We get entropy from the sun. So sun sends us higher frequency wavelengths, shorter frequency light. We take one like ultraviolet, we use it, we let it work for us because there's work, and then send 25 infrared photon out. We get a one high energy photon. We let that high energy photon work for us, and then send back to space same amount of the energy, but in lower frequency infrared.
This is just like we eat.
That's exactly what it is. So how much?
We're a prism. That's
okay,
all we are.
so not me, but you. How much of the food are you keeping in you?
Dude,
Zero.
I've done some calculations. I consume around 5,000 to 6,000 calories a day, and I swear I don't have like an adrenal.
How much of the food are you keeping?
Probably none of it.
Because you weigh yourself. Even if you would keep, let's say, you eat like 3 pounds a day, something like that.
I feel like that's a low budget, but yeah.
Okay, let's say you eat 5 pounds. Okay,
like that, yeah.
You eat 5 pounds. You keep 5% of it every day. Every single day, you keep 5% of it.
We can't fit you in this room now.
we couldn't. The same thing with the earth, you know?
Yeah.
The same thing what we get from the food. We don't get really their energy. We get the entropy. And energy is what we call energy is actually order that become disorder, and that while the order become disorder, it does work for us, keep our biology going.
It brings disorder to our body and then
No,
peace out.
the order, we use it, we make order from the sun to disorder, and that from order to disorder, like water at the higher level coming down, that does work for us. And same concept of the entropy as well explain to us why we understand the time in one direction, because it never, the 50 infrared photon never come together. There's a caveat there. Never come together to make a one ultraviolet thing. Now that 50 never come together, become an ultraviolet photon, go back in the sun's direction.
So what I've gathered is very philosophically, as a species and just entities in general, we take order and create disorder. That's our number one product.
That is a caveat. The only thing in the universe works against that and makes from disorder order is biology. But it's not like we make, so see, it's not like we take the disorder, make it order. We get the order from, we get 100 unit of order from the sun, and then use that 100 order from the sun to make 2 unit of order from disorder, and the other 98% we just, it is like any other machine. In the universe, that is some of the concept that they say, okay, but how is there order if the entropy and the first law of thermodynamics is true and everything goes toward disorder? How life happens? Why is it so much order? No, you can make out of disorder order locally if you are using higher level of order from sun, for example, to make bigger amount of disorder. But it's always higher level of disorder, higher level of entropy, and it's hard for our mind to really calculate that, but that's what time is. That's what truly time is. And that passes at different intervals for everybody. We know that with the space and so on, it all works in a different way. But it's always something that more higher level of energy, higher frequency become lower frequency. Like, what's the temperature of universe? 3 Kelvin. Universe is very, very cold. But 3 Kelvin, then we have a sun temperature of like millions of Kelvin in the core. That from millions of Kelvin to become 3 Kelvin, that is time. And one day in the universe, time will, no matter where, will disappear, because the whole universe, everything goes and goes and goes, becomes less and less and less universe. That's what the expansion of universe is. Okay? Things are going to matter less and less because there will be more and more entropy. Everything becomes equal. So when water falls, that was one of our first clock. We let this water come down, drip, 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 drip. Yep. When water don't drip anymore, when pendulum doesn't swing anymore, when there's no more energies gathered in that winding of the clock and so on, when there's no more battery in that, because all of that works from higher order to lower order, when all of that stops, time becomes meaningless.
Which makes sense, because just like you were saying with the Chicago to Minneapolis, right? You notice the change of time. Time passes because there is change. If everything's stillness, there's no change.
And you're burning gas.
Yes.
To make that happen, okay?
So
you're using the higher order of the gasoline to lower temperature that your exhaust are to make that change happen.
Yeah, I need that tiny bit of order to get moving.
Yeah.
And eventually, when I have none left, well, I mean, if nothing changes, then all of that, gone.
Yeah.
There's no time.
It's just gone.
Yeah. And that's not, look at how we use the time. You have to be in places. You have to keep things. If there is no energy to do anything, like we are meeting here to use the electricity to do a podcast. If there's no energy to do the podcast, you don't have to be here on time. Time means less and less,
Yeah.
Okay, well, this is become a lot philosophical. We haven't even opened the door of where this is the kindergarten level of time. We could talk a lot more about entropy, time, and how they are intertwined and why it matters for us in our actual life, like GPS, but as well philosophically about what is the future of the whole universe.
Mhm.
So, but I think this is a good place to stop. Okay.
I think a series of time. Like,
Wait a minute. If we stop, if we just don't use energy anymore.
I'm going to tell you something that's very interesting. Okay.
Yeah.
How long does it take how long does it take for human to go to moon? Apollos. How long did it take them to go to moon? 3 days. How long does it take our space craft go to Mars? About 6 months.
Okay.
If they go faster, obviously it takes shorter amount of time.
Yeah.
If you could travel at the speed of light, how long would it take to go to sun? 8 minutes 20 seconds. How long would it take to go to moon?
Depends where the moon is, right?
Yeah, more or less a second. It's about a second to go to moon and back. Okay. Now, meaning that star that's 4 light year, even if you're as close to speed of light that you can be, it takes 4 years to get there.
Yeah, all the stars is just the past. Maybe they are gone already.
Yes, you see always their past.
Mm.
You see their past. Now, how long does it for that photon from that light takes to come to your eye? To you see it? You see a star in the night? That star is maybe 1 billion years away from us, or millions of years away from us, in a different galaxy, because we know most of the stars you see is in the Milky Way galaxy, which is about 230,000 light year and so on. Okay, 200,000 years on the other side of the galaxy, you see that light of that star left that star about 200,000 years ago, hitting your eyes right now. Whatever you see is 200,000 years ago. How long does it take for that photon, for that, not for you, for that photon to hit your eye after it leaves the star?
Exactly the age.
Now, do you remember space-time?
Yeah, it's
Faster you travel in the space, less in the time. So, meaning that if you're traveling like 70% of the speed of light, meaning you have to travel really fast, you slow down like significantly, like time is slower for you.
Yeah.
If you're at 99% of the speed of light, like your second is like almost 5 seconds or 10 seconds for me or so. There's a formula for that. What about what speed that photon is traveling at?
That is
That-
nice.
Yeah.
Speed of light.
yeah. So that photon experience is very, very little.
Very little. How little?
If it's a 1-to-1, then nothing.
0.
That photon just went.
Okay.
Hey, I
that-
woke up today and
It
here I
took,
am.
it took for you 300,000 years for that light to come from other side of the galaxy to you. For that photon that hits your eye, that happened just that instant. He left that star right now for that photon. Because time doesn't have any meaning. When you are at speed of light, time has no meaning.
So, Jimmy, I know you dreamed of time travel. It's not possible to the past that we know of. But if we
Time
get
travel
you
to-
going fast enough, you can go to the future.
I can stay right now. I can stay here.
So, and that is that's the magic of it. The star that you see that is already gone, like the million of years ago, sent the light to your eye. That photon, that leaving that star happened for that photon instantaneously.
I'm
Just
confused.
that had no time has passed for that photon. That star, he was in the star and he's in your eye at the same time.
Jimmy, imagine you're the photon, right? You're just a little photon. Whoa, ooh, I'm a photon.
So I'm gone, but
You're
at the
in
same
the-
time, I'm here.
You're here.
Yeah.
Do you
Yes.
see how confusing that is? Because
Meanwhile, 200 or 300,000 years have passed.
because all the space-time thing in that photon goes to space, and zero of that goes to time, and that is why we cannot reach the speed of light. Okay, for matter, it's not possible for particles who have mass to reach speed of light, and that's why photons are massless.
Yeah, basically, Jimmy, if you could go to Mars at the speed of light, it'd be a nice little trip for you, right? You'd still come back and a lot of time would have passed.
Yeah,
You'd be behind on all your work.
Photons, and that's the magic of it. Photons are everywhere at the same
Lucky little guys.
time. That's okay.
I need to watch Back to the Future.
So, for essence of science, we talked about the time. I'm Dr. Abbasi.
Dominic Moore.
I'm Jimmy.
Okay, thank you.